Welcome to our first lesson of probability and statistics. In this lesson, we're going to be covering chapters 1 and 2, specifically working from the book Elementary Statistics, 4th edition by William Navidi, published by McGraw-Hill. In this lesson, we're going to be covering, in chapter 1, sampling methods. So how do we collect data in statistics? What are those different types of data that we can collect? Talk specifically about experimental design and what that means and why that's important. And then bias in terms of what are some things that we need to be careful of and watch for as we collect and analyze data that could skew the results from kind of what would be objective. And then chapter 2 is all about graphical representation. How do we take that data that we've collected, how do we visually represent it and present it to our audience in a way that makes sense to them and that they can understand the data being presented. So let's go ahead and get started here. We're going to start with the definition of statistics. And statistics, I'm going to say it this way, is just simply the study of procedures. So study of procedures for collecting, describing, and drawing conclusions from information or from data, if you wish. And so when we think about statistics, yes, it is math-based. There are mathematical formulas that we use and calculations that we make, but statistics is really so much more than that. A lot of statistics is just after we've gotten that data, we collect that data, and that's an important part. We're going to talk about that in this lesson. What do we need to be careful of? What do we need to watch for and think about as we're simply collecting that data? And then it's doing the analysis, doing some of that mathematical work. But a lot of it then is what do we do once we've done that? Who is our audience? What kind of information are we ultimately trying to get from the data? How are we going to present it? How are we going to communicate it? Things like that. So a lot of what we do in statistics revolves around the idea of analysis and communication. Those are two critical parts of statistics as we think about using that in practical ways, in ways that are going to make the data useful to ourselves and or to others. So let's go ahead and talk about then how we collect data, how we sample to get that information that we need, that we can start to synthesize, analyze, and communicate out. So when we think about data can come from two different places, I guess we can kind of say it that way. The first is the population, which would be your entire group. So when we think about collecting data from a population, a lot of times we might think of a population as a population of a country or maybe population of a city or a state, something like that. When we talk about population, though, what you define as the gatherer of the data, what that population or who that population is going to be. Maybe you want to know something about M&Ms. So M&Ms could be your population. It could be all M&Ms in the world. It could be M&Ms in a particular region of a country, something like that. You might be concerned about pencils being produced in a particular plant. So the pencils at that plant or coming out of that plant is your population. Obviously, it could be people. You might want to define your population as all citizens of the United States, or maybe as all residents of Wisconsin or all residents of New York City. So you can define that population however you want, and then that population is what you are studying. It's from that population that you are going to collect data. It is that population that you are going to hopefully and that you're trying to make generalizations about. And so that's where our sample comes in, because a sample then is simply part of that population. Now, ideally, if you're trying to get information about a population, the ideal would be to kind of have a touch point with every single individual in that population. In many cases, that's not possible. In some cases, it is. If I'm concerned about, if I want to, maybe I want to poll a group of, all students at an elementary school. Well, it's possible that I could ask every student in that school whatever questions I have for them. It's possible that I could address the entire population. But in a case where I want to get information, from everyone in a country, that's not going to be possible. And so that's where the idea of sample comes in, where I take a sample from that larger population and then use that sample to make predictions and estimates about what I believe the entire population is thinking, or what is true about that population. So we'll get more into that in a minute, and that's part of that whole sampling method. How do we collect, how do we create that sample so that we can make those inferences about the larger population? Also, then, we want to talk about parameter and statistic. Parameter is just any value that describes the population. And a statistic is any value that describes the sample. In statistics, we want to be very, very clear about which group we are referring to. If I'm talking about the mean of a population and the mean of a sample, there are two different symbols that we use depending on which group I'm talking about. Same with standard deviation and so on. So it's important that we make clear, is our information, is our data, our numbers referring to the population, or are numbers referring to the statistic? Okay, let's talk about those different ways of sampling that I referred to earlier. And there's other ways to sample as well. These are kind of just some of the more, I guess, major ways or more common ways. The first and foremost is just what is called a simple random sample. In a simple random sample, you are going to take all of the elements and you are going to number all of the items, whether it's people or things or whatever, 1 to n. N being then the population size. Then we're going to randomly generate n unique numbers from 1 to capital N. Okay, so the idea here is maybe, so let's take a city of 10,000. I want to know something about the city, about how its citizens believe or are, the opinion they have about something. So I take all 10,000 citizens, I number them 1 to 10,000. And then in that second step, maybe I'm going to sample 500 of the people in that city. So I generate 500 unique numbers from 1 to 10,000. And then I select corresponding items. In this case, people, but it could be actual things, depending on what your population is, what you're studying. And those are going to be my sample. Okay, so I take those 500 people, and those 500 people become my sample. Now, in a simple random sample, that can be daunting because I have to, somehow, obviously through some kind of computer program or some kind of database, I have to, have access to the names of all of those people. And then I have to randomly generate the 500 numbers, select the 500 people, contact those 500 people, and so on. So a simple random sample is exactly that. It's simple and it's random. And one of the things we want to be sure of is no matter what method we use, we do want randomness, because that's going to help ensure that we're getting a better cross-section of the population that we're studying. Convenience is not random. Convenience is where we take a sample that is convenient. I know I'm using the word to describe the word, but it really is, that's exactly what it is. So I may stand outside of a store at the mall, and as people come out of that store, I ask them, whatever question I have to ask them. I may go to, maybe I want to survey teenagers, so I go to a local high school, and I ask if I can, have the students take a survey during a study hall or something. Okay, so it's convenient. The problem is that depending on what your population is, you may constrict your sample too small and you're not getting a broader representation of the entire population. If I go to a single high school and ask those teenagers a question about something, I can't use that to generalize to all teenagers because I didn't ask a cross-section of all teenagers. I just asked at that one singular high school. So convenience is typically neither random nor a very good way of really being able to generalize to a broader population. Voluntary response is where people can choose. So this is going to be specifically when people are involved. People can choose to participate. And this actually isn't really let me finish this thought. People choose to participate as part of a sample. As part of the sample. This is not really a sampling method. This is more kind of a subset within. So for example, if we go back to that simple random sample idea, I may select 500 people to be part of my sample. But if I just send everyone a letter in the mail saying, here's a questionnaire, please fill it out, send it back in the self-addressed stamped envelope, or maybe I send an email, would you please respond? They can choose whether or not they want to participate. So again, the problem here is that maybe I did a really good job of making sure that those 500 people represented a cross-section of the 10,000 people in that city. But if I allow for voluntary response, it's possible that certain groups or characteristics within that group are not going to respond. So to make it very simple, maybe all of the females respond and none of the males respond, or very few of the males respond. So now my data is very skewed. It's not broadly represented of the population because I'm missing out on a key demographic in that population. Now, depending on what the question or information is that I'm gathering, that may or may not be as important. But if gender is going to be a factor in how people respond, then that's going to create problems in my data. All right, systematic. This is where we select every nth item. So a lot of times you'll see this more like in manufacturing, for example. So as parts come off of the line, whether it's a part or a finished product, maybe every fifth element is selected. Okay, and then this quality control comes through. Every fifth car that comes off the line, they're doing a comprehensive test on that to make sure that it's everything is constructed well, is put together properly. That would be a systematic sample. Stratified is where we divide the population by characteristics. So this kind of gets back to what I was talking about earlier, where the voluntary response may cause certain parts of the population not to be involved in the study. In this case, if we divide the population by characteristics into what we call strata or groups, then those strata would represent what we believe to be important factors in the outcome of our data. So again, for example, if I believe that gender is going to have an impact on how people respond, that females may respond differently than males, or if I believe that age has an impact, that younger people are going to respond differently than older people, or if I believe that wealthier people are going to respond differently than poorer people, or so on and so forth, then what I do is I take those strata, the gender, the socioeconomic, the age, and so on and so forth, and I specifically target different groups within those. So for example, I may take male, female, and I'm going to try to sample an equal number of male and female. I may try to sample an equal number of older and younger people in the population, or whatever the case may be. And so we're taking those characteristics And we're cutting across those characteristics. So if this is age, maybe I want some in their 20s and 30s, 40s and 50s, people over 50. And so I'm trying to get a cross-section by strata, by characteristic, so that my sample as a whole broadly covers the population, that I have a mix of all those different demographics that I believe may impact the outcome of my results. It's harder to do, it takes more energy and effort, but it's a much more accurate way of making sure that we've really gotten a broad cross-section of our population, especially when people are involved. There's certain situations where this is not as important, but certainly some that are. And then cluster, this one has kind of a similar vibe to stratified, though it is quite different. But we're going to divide the population into groups. And then we randomly select groups. So in this case, what happens is I'm not taking a characteristic and cutting across the different elements of that characteristic. I'm just taking the population, I'm literally slicing it into, almost think of it as geographic, like just different parts, and I'm grabbing whole sections out of that population. And then those become those randomly selected groups, I'm going to sample all items in the selected groups. So let me kind of give an example of this. Let's say, for example, that I want to know something about all citizens in the United States. In a stratified, I may, for example, try to stratify across gender. I may try to stratify across region of where people live. So looking at that second idea of region, maybe I randomly sample 50 people from every state. And that way I've broadly cut across all parts of the country. In a cluster, what I would do is I would instead think of each state as a group or a cluster, and I would randomly select, let's say, 5 different states, and I would sample every person in those 5 states. Now, obviously, that's not practical, but that's the idea behind a cluster. Is I'm not cutting across and looking at all the individuals across all of the elements or all of the groups. I'm grabbing groups and looking at all of the individuals in those groups. So those are just some different ways to sample. Again, key here is you want to be random when you sample, and you want to try and really make sure that you've got a cross-section of your population when you sample, because that's going to allow you to better predict or infer what you believe about the larger population itself. All right, let's move on and talk about some different data types then. So we've talked about how to collect data. What are some different things to think about in terms of the types of data? Because that's going to potentially impact not only how you sample, but more importantly, how you then display and present that data that we're going to talk about in Chapter 2. So there are 2 types of data that we generally kind of put our data into. There's qualitative and there's quantitative. Qualitative is basically what I think of as buckets. If you can put your data into buckets, it's likely qualitative. For example, color. If I want to go around and ask people what their favorite color is, I can put that into buckets based on blue, red, green, orange, and so on. So I may have 42 people whose favorite color is blue, 37 who say green, 14 who say yellow, and so on and so forth. So it's a situation where you can typically count the number of occurrences. That's a number sign, the number of occurrences by category. That's typically how you're going to think of quantitative. Qualitative. Quantitative, on the other hand, are typically values. They're things that are often measured. So things like height, weight, distance, all that sort of thing. A lot of times we think about, I was going to give an example, but it's a confusing example, so I'm not going to give it. But that's the idea. So a lot of times just anything that is going to be a little more continuous in nature is going to be, and we're going to talk about continuous discrete in a moment, but that's typically your quantitative. Ordinal, nominal, not so important, but I do just want to point this out. Ordinal is any time, this is specifically with qualitative data, so again, think of your buckets. If your data is ordinal, you're saying that order of the categories is important. So order of categories is important. So saying blue, then green, then red is important if that is going to be different than saying red, then blue, then green. Okay, so that's ordinal. And then nominal is when it's not important. It doesn't matter what order I put those colors in, so on and so forth. Let me give you an example of this. So, for example, in an election, candidates want to be at the top of the list on the ballot because statistically, people often vote for the candidates that are higher up in the list. So if you've got 7 candidates for a position, maybe it's something like city clerk, and you've got 7 people who are running for that, typically it's those people at the top of the list who are going to be voted for more than the people at the bottom of the list. So the order that those are presented in is important, okay? If I'm asking people favorite color and I'm saying, is your favorite color blue, green, red, or yellow, it doesn't matter what order I give those colors in. People are going to have a favorite color regardless. Okay, they're not going to go, oh, you said yellow last, and that's my favorite color, so maybe I'm going to say blue instead, right? That's not going to happen. So order's not important there. All right, discrete and continuous. This is kind of another big idea in terms of data and thinking about data. Discrete is when we have separation between values. So a lot of times thinking about whole numbers. Now, I hesitate to say this because it's not always whole numbers, but oftentimes it is. It's often going to be your counting numbers that are going to be discrete. Okay, continuous then is where you have numbers between numbers. Now, it is possible, if I go back and talk about qualitative, quantitative, it's possible that qualitative could be discrete or continuous, and it's possible that quantitative could be discrete or continuous. A lot of times what you are going to find, though, is qualitative is discrete, quantitative is continuous. Again, not always, but there's often a correlation between those two. All right, and then ratio and interval levels of measurement. This really just has to do with the idea of how do we treat zero. And I know that sounds kind of funny, but how we treat zero is kind of important in terms of thinking about our data. So a ratio measurement is where zero is the absence of something. So for example, if I am asking people about how many children are in your family. Maybe I'm trying to get demographics of a city or something. I want to know how many children are in a typical family. 0 would mean there are no children, right? There's an absence of children. Whereas interval levels of measurement simply mean that 0 is just another possible value. So for example, temperature. It could be 20 degrees above 0. It could be 20 degrees below 0. It could be 0 degrees. 0 degrees is not the absence of heat or cold. It's not the absence of temperature. It's just another value on in this case, a rating scale of cold to hot. So that's ratio of intervals ratio of measurement and interval levels of measurement. Okay, let's talk about experimental design now. So experimental design is really an important concept for two reasons. One is It's how we often will collect data when we're really trying to show causation. We're trying to show that one thing actually causes another thing to happen. The other reason that experimental design is important to talk about is because how we design that then is important to ensure that the data we're collecting is accurate, and so that there's validity behind our data, so that we can make those causations from one thing to another, and also to be sure that we're ethical in our experimentation. And even, a lot of times when we think about ethics in experimentation, we think maybe about, how animals are treated, how humans are treated, things like that. But even just a poll, for example, could have ethical implications in terms of how I ask the question, what wording I use in the question, things like that. So experimental design is a kind of a big topic here, and so I want to just make sure that we really understand how this works. So we're going to kind of do this through example for this one. So it says a pharmaceutical company wants to test the efficacy of a new drug it has developed. Researchers at the company select 1,000 individuals to take part in the study. So that's kind of our setup, right? So a company wants to know, is their new drug effective or not? And they're going to select 1,000 individuals to take part in the study. So we're going to use that to help us understand all of the terminology now that we're going to go through. So the experiment is a situation where there's a treatment imposed. So in this case, we can assume that, for example, we're going to have two groups. One group is going to get a drug, the other group might get a placebo, and we're going to see if the drug actually has a sizable or measurable change in efficacy versus the placebo. So experiments, we impose a treatment on people, on things, on whatever it might be. An observational study is different. This is where we simply observe. Again, I know that's right in the word, but we observe or collect data without any influence. And I'll specifically say without our influence. In other words, I am simply kind of on the outside looking in, gathering data. I might be going back in time and collecting data. I might be collecting data in the present. I might be collecting data now as a baseline, and I'm going to collect data in the future to do a comparison. But I'm not actually imposing any kind of treatment. I'm not doing anything that would intentionally cause a change in the data itself. Whereas an experiment, I am imposing that treatment with the intent that that treatment is somehow going to change the data. I expect that when I give those patients that drug, that it is going to have the desired effect on that person. Okay? So the experimental people then, or experimental units, are the target of the treatment. Again, doesn't have to be a person. Maybe I want to test different materials to determine which maintain heat the best. So I'm a large food chain company, and I want to know what's the best way to serve coffee. Do I serve it in paper cups, in styrofoam cups, in plastic cups? How do I serve it that is cheap, but also maintains the temperature for a long time so that people 20 minutes later are still drinking warm to relatively hot coffee? When we do involve people, a lot of times we will call those people subjects. So the subjects of the study, for example, or the experiment. All right, the treatment is what is being imposed on the experimental unit. So in this case, again in our example, the drug is the treatment. We're going to give the drug to one group, maybe we give a placebo to the other, but that treatment then is what we're actually giving to or doing to the person or thing in the experiment. The response is simply the outcome. Do we see a difference or not? Do we see a change or not? Another thing to think about in terms of experimentation, again, this is particularly important when people are involved, when people are the actual subjects or the actual experimental units that we talked about earlier. So blind means that the subjects don't know which treatment they're receiving. So this again is particular for people, so subjects, that they don't know which treatment they're receiving. And this is important because, again, of the whole placebo effect, right? So if I take a drug, I take a pill that has no actual active ingredients in it, but I think I'm taking a pill that's going to, for example, take away my headache, my body, believing that I'm taking a pill to take away my headache, can actually get rid of my headache, right? It's that placebo effect. So when we give these two treatments, that's why you often want two treatments. You want the drug and you want that placebo, because you want one group to actually get the drug. You want the other group to get the placebo, believing that they're getting the drug. So that now both groups think they're getting the drug. Both are going to respond in a similar way. One, however, is actually getting the active ingredient. The other is not. Is there a measurable difference in outcome between those two groups? In a double blind, neither the subjects or the people administering the treatment don't know which is which. So I'm just going to focus on the latter part. So the person administering the treatment, doesn't know. I'm just going to say which is which. So in this case, they don't know if they're giving the drug or the placebo. And again, that's just so that through nonverbals, through our body language, we don't accidentally tip off to the subjects which one they're getting. Okay, so there's no possible way, if I, as the person administering, handing out the drug, handing out the placebo, if I don't know which is which, there's no way that I can possibly insinuate, infer, communicate in any way to the subject which one they're getting. Okay, so again, double blind isn't always critical, but it just, again, it helps keep everything very, very objective. Obviously, the person behind the screen is going to know, which one is which. They're going to know that the people in room A got the drug and the people in room B got the placebo, and so on. So somebody knows, just not the person actually handing it out. Okay, the other thing to think about then when we think about experimentation is confounding variables, or what your book calls confounders. And this is anything that affects the results. Anything that affects results outside of the treatment. So as we talk about the actual design of an experiment, we're going to talk about how we mitigate those confounding variables. But again, if for example, I'm testing a drug, maybe I'm testing a drug that takes away back pain, okay? And maybe, there's certain variables that I want to account for because I believe that those could impact. There's ways that I can mitigate that. If I am, for example, maybe I'm working with teenagers, and I want to know if I offer an ACT prep course, will that improve ACT scores? Well, if I offer an ACT class and just ask, students to volunteer to take it, and their scores go up, I don't really know if it's the ACT class, because maybe those are the students who are highly motivated and they were studying anyway in the outside of class. Maybe they're the ones that are really smart and would have done much better on the ACT anyway. So I don't know if the class itself caused the increase or not, because there's other variables, other confounding variables or factors that may be contributing to their higher scores than just the class itself. So these are the things that we want to be aware of as much as possible and try to mitigate as much as possible so we can pinpoint any changes to the actual treatment itself. Okay, so let's talk then about how we actually design an experiment. And so this is where I'm going to go back now to that setup that we had before. So let me go back to this. So we've got this pharmaceutical company. They want to test a drug. They want to know if it's effective or not, and they're going to select 1,000 individuals to take part in this study. So we're going to talk about really just one way, and then I'll mention another way that you could do this. Basically what we do is we're going to take those 1,000 people, and I should mention, by the way, in an experimental study, I mentioned ethics earlier, you can never force somebody, obviously, to be part of an experiment. So everybody has to volunteer. They have to know exactly what they're getting into. They have to know what the experiment is for. Now, there are certain things you could maybe withhold that if you're afraid that if you let them know that it's going to impact the results. But for example, I certainly have to tell them I'm giving them a drug. I have to tell them, in this case, I would have to tell them why they're taking the medicine. So there's certain ethics behind this where they have to volunteer and all of that. That's also why, like in academic research, you have what's called an institutional review board, because that IRB, that institutional review board, will actually look at your proposed study to determine and make sure that everything is on board, on par, is on the up and up, is ethical. Anything in there that they believe, in how you are selecting participants, in what information you're giving participants, what you're going to do with the participants, if any of that is even remotely questionable, they're going to come back and say, we need more detail on this, or you need to change this, or you can't actually do the study. And again, academically, it's tied to a university. You can't do the study. You can't publish the results. It's not going to be worth anything. So, all right. Anyway, getting back to our randomized block experiment, we're going to divide the experimental units into randomized groups. Randomization is always an important part of statistics. So we're going to take our 1,000 people and we are going to randomly put them into, let's say, 2 different groups. The way that we randomize them is not important. We could number them 1 to 1,000, generate 500 unique numbers, and those first 500 unique numbers are in group A, everybody else is in group B. You could flip a coin. If it's heads, you go to A. If it's tails, you go to B, and we do that until you've got 500 in A. Everybody else goes to B. Numbers or names in a hat. How we randomize doesn't matter. We want to randomize, though. The reason we want to do that is because when we take those 1,000 people and we apply that random assignment, when we randomly assign them to one of those 2 groups, we are mitigating a lot of those confounding factors. Age, health, gender, all these things that could impact the efficacy of that drug are mitigated, because by randomly assigning, we are assuming that the 2 groups have roughly equal groups of, or equal number of people with those characteristics. So group A and group B, we expect to have both roughly the same number of healthy and unhealthy people. If we believe that gender somehow is an impact on the drug's efficacy, male, female, all that kind of stuff. So we randomly assign. Group 1 is going to have 500 people. Group 2 is going to have 500 people. And then group 1 gets treatment A. In this case, let's say treatment A is the actual drug itself. Group 2 gets treatment B. In this case, the placebo. And then we actually compare the results. How did group A or group 1 respond to treatment A? How did group 2 respond to treatment B? Is there a statistically significant difference in how those 2 groups responded? If there is, we can make the claim that it was the drug that caused the difference and not something else. Okay. There's also what's called a matched pairs design. And by the way, there's different ways to do this. There's multiple ways to do this. Matched pairs is another one where let's go back to the ACT example. So maybe I have 100 students who volunteer to take the ACT prep class. And if I believe that how students do in school will impact how they do on the ACT, that students with better grades will do better on the ACT, then what I could do is I could take, for example, the 2 students who have volunteered with the highest GPAs and flip a coin and randomly assign one of those 2 students to group A and the other student to group B. And then I take the next 2 highest GPA and I do the same thing. I assign one randomly to group A, one to group B. So that when I'm done, I have roughly, that I've got these 2 groups that are mixed from high to low GPAs, but for every two, again, I randomized which way they went. So it wasn't always the higher GPA of the two that went one direction. It's all randomized, okay? Going back to the first experiment, the 1,000 people, again, if I believe, if I'm concerned about, let's say weight, if I think weight is going to have an impact on the efficacy of this drug, I could, instead of doing two groups, I could, for example, let me do this down here, I could take those 1,000 people and I could split them up into two groups. And maybe I take, maybe it's much like what I just talked about, the matched pairs, or maybe I take the 500, healthiest. I'll just use healthy instead of weight, and the 500, not healthiest. Okay. And then what I would do, and this is maybe not the best example, I'm kind of doing this off the top of my head here. Those 500 get put into groups A and B, one getting the drug, one getting the placebo. The second group of 500 also get put into groups A and B, so that I can compare how did these two groups with the drug do against these two groups with the placebo. And so I'm still comparing those results at the end, but now I've ensured that the factor or factors that I believe could have the biggest impact on outcome are randomly distributed through the groups who are getting placebo and getting the drug. Okay, hopefully that makes sense. Different ways to set these up. Again, you always want to be random, and you always want to be thinking about what are those factors that could impact results, and how do I mix those factors into the groups to make sure that the treatments are being spread across those as evenly as possible. All right, let's talk about observational study just a little bit. So we talked about experimentation, where we apply a treatment to show causation. Observation is not about showing causation, it's really more about showing correlation. If I look at just kind of what's happening, can I see a correlation between one thing and another? Perspective looks to the future. So I select a group today and I kind of follow them along as they progress to see, what maybe I'm studying dietary habits and how does that impact health. So I'm looking today at their health. I'm going to follow them for the next 10 years and they're going to track kind of what they're eating. I'm going to follow their diet, and 10 years from now we're going to see if there's any health differences between them and if we can see any correlations between their diet and their health. Cross-sectional is a kind of a moment in time. So in kind of following the same type of example, maybe I just take 1,000 people and I ask generally, what is your diet? What kinds of foods do you generally eat? How many calories do you generally take in? Things like that. And then let's take a look at your current health and see if there's any kind of correlations that we can see. And then retrospective looks to the past. What was your health like 10 years ago? How has your diet looked over the last 10 years? What is your health today? Again, correlation, that sort of thing. And then what's called case control. This looks for differences in two groups to make conclusions about possible correlation or causation. To make conclusions about possible causation. So this is where, again, I'm being more specific in actually trying to, it's a little different than experimentation, but I am trying to control somewhat in how I group people or pick people or things like that to try and see those correlations or those causations as we look at that data. So those are kinds of the way we do experimentation, how we set up an experiment and collect the data through experimentation, a little bit about how a study would look. Okay, let's go ahead and finish up Chapter 1 by talking about bias. And then we're going to get into Chapter 2 just very briefly and just talk about some visual representation. So bias, I I'm not going to really write too much down here. I'm just going to kind of talk through these. They're pretty, I think, self-evident by their names. We talked about voluntary response already. This is where people can choose to respond. Again, the issue is if I have a certain characteristic of people within that group who don't respond, I'm not going to get necessarily the cross-section of data that I was looking for. Self-interest is where, again, this can go a couple of different ways, but self-interest is where typically the people responding have a self-interest, so they're going to respond if they have a strong opinion, things like that. I also, as the person giving the poll, may have self-interest in what I want the responses to be, so I may intentionally or unintentionally use wording that is going to cause people to respond more one way than another way. According to a leading university or according to a researcher at a leading university, watching too much violence on TV has caused children to bully at school. Do you believe violence should be on TV? Right? So I can use leading things on my questions, and that's one of the things down below that we'll talk about. But I may have a self-interest in how I want the responses to occur, to come back to me. I may inadvertently do things that cause that to happen. Social acceptability, kind of the idea of what do I think I should say versus what is actually my opinion. Leading question, I just gave an example of that. And the non-response is different than voluntary response. Voluntary response is that idea that I can choose. Non-response is a little bit different because non-response is not just about not responding. It's not about the voluntary piece. It's more about when I can't actually access all of the people. So, for example, I wanted to do a survey in a city, and so I look at landlines, right? I'm going to contact all the people with landlines. Well, guess what? Most people don't have landlines anymore. There's a lot of people I won't be able to contact in this study because of that. Or maybe I only make phone calls from 9 to 11 in the morning. Well, if people are at work, even with their cell phones, they may not pick up because they're in meetings, they're busy, they can't be contacted. So non-response is more about not being able to reach the person for one reason or another versus the person choosing not to be part of the study. All right, that is all of Chapter 1. Let's jump into Chapter 2 and let's talk about graphical representation. And again, there's not a lot that I'm going to really dwell on here because I think a lot of this is probably something you already know. We're familiar with things like pie charts, bar graphs, and things like that. But there are some that I do want to focus on a little bit more than others. So some of the qualitative, and I guess one of the things I should mention is when we talk about graphical representation, we talked about type of data before, and in particular the idea of qualitative versus quantitative. This is going to determine oftentimes what type of graph or graphs are available for use. So there are certain representations that we would only use for qualitative. There are certain representations that we'd only use for quantitative. One of the things also to think about is your audience. So as you think about who is going to see the graph, the visual, the table, whatever it is, who is going to see it and what is their level of knowledge, mathematical, statistical, so on, so that you pick a representation that's going to be at an appropriate level for them. If it's a group of people who are in the field, who understand graphical representations, who understand data, you may want to use a representation that's more in depth, more revealing about the data, tells a bigger story, versus if I'm just publishing it in a newspaper for the average Joe on the street to read, I might use things like pie charts and bar graphs that are easier to understand, quick to look at, and get the information right away. Okay? All right, frequency table. Frequency, when you hear that word, I want you to think counts, because that's all it is. So it's just a table of counts. So if I do a frequency table for M&Ms, I might have brown, red, green, so on and so forth. And a frequency table is just going to be a count of how many different M&Ms I see from a bag, or whatever the case may be. When you see the word relative, think percent. So relative frequency distribution is a percent. So again, and I'm going to use a different example here. Well, slightly different. We're going to stick with our M&Ms. Maybe it's red, blue, and yellow that I'm looking at. And so instead of a count of how many, I'm looking at a percentage. So maybe 30% were red, maybe 35% were blue, and 35% were yellow. Okay, but these are percents, not actual numbers. And so this would just literally be a table. It's not a graph. It's just literally a table with categories and numbers, or categories and percentages. Bar graphs. I think we all probably know what bar graphs are, but there are a couple things that I want you to just be aware of. On a bar graph, when we make a bar graph, these are buckets, right? So this is going to be different graphs for each bucket. This might be red and blue and yellow for our M&Ms. In a bar graph, there is separation between those bars because we want each bucket to be distinctive from the other. One bucket is for red, one bucket is for blue, one bucket is for yellow. Each of those bars represents a different bucket, and obviously on the vertical axis, you've got the count or percent that you're using. I'm going to skip Pareto chart. We don't need to know that one. But pie chart is basically then where we have, obviously, again, you've got maybe yellow, blue, and red. And so this is red, blue, and yellow. And this is 35%. I don't remember what the percents were. I'll just make these up. Okay. And so you've got the different percentages. Obviously, in a pie chart, the entire pie represents 100% of your data. And so here, we're always dealing in percents. Each piece of the pie representing a percentage of that entire pie that the data represents, that bucket represents. So all of these types are all qualitative that we're dealing with here. Okay. All right, let's talk about some quantitative ways to do this. So a dot plot it's a cumbersome one, but it's kind of a nice way to show data because you actually see all of the individual datas. So maybe I've collected data about heights of giraffes, and I've got all of these different dots, and the dots represent the different heights of giraffes that I've sampled. Okay, so you can see what the heights are, you can see how many were in each height, so on and so forth. Frequency and relative frequency. That is similar to what I showed on the front, but here a difference is that these are actually. I'm sorry, I'm thinking of the relative frequency. I'm going to skip this. We're going to skip this one because I want to talk about the frequency polygon down below. But let's talk about the histogram first of all. Histogram is like a bar chart, but it's different because here we still have count on the vertical, but in this case our bars actually connect. The idea here is that you want this idea that because it's quantitative, that the data is continuous, those values are continuous, so they're ranges. So this might be a height of 4 feet to 5 feet to 6 feet to 7 feet to 8 feet, whatever it is that I'm measuring, right? So that this bar represents 4 feet to 4 feet, 11 inches, and then this next bar is 5 feet to 5 feet 11 inches, and so on and so forth. So they're groups of data, not categories of data. I've taken my continuous data, go back to the height in my dot plot. Maybe this is one bar that I use to create. This is another bar. This is another bar. This is another bar. And so those bars just simply represent how many items or elements are in a range of values. All right, the frequency polygon. So this is where basically what we're going to do is we're going to take our frequencies. So let me go back to, again, kind of that, well, we could do this. We could do this for I'm going to do this for heights. So let's take our 4, 5, 6, 7, 8 heights, and I'll just go up to 7. In this case, what's going to happen is maybe 4 feet represents 20% of our data. 4 to 5 represents another, 30%. So now we're up to 50%, and we're just going to draw a line to that. And then maybe up to 6 feet takes us to a total of 65% of our data, and then 7 feet takes us to 100% of our data. Okay, so you're literally just, it's almost like a cumulative table where you're taking those percentages, and maybe it's 20, 30, 25, and 25, but on the graph, it's 20, 50, 75, 100, because you're literally looking at the total as you go along. Okay. All right, ogive is basically another frequency polygon. It's basically the same thing. Stem and leaf. So let me just make up some data here. So I've got data 64, 57, 49, 47, 62, 58. And what you're going to do here is you are going to create a stem. So this may be the tens column. And then I'm going to just look at how many 40s I have. I have a 47 and a 49, so I'm going to write 7 and 9. I have a 57 and a 58, so I'm going to write 7 and 8. And I have a 62 and a 64, so 2 and 4. So kind of the key here, if you will, is that a 5, 1 is 51. The numbers on the left side are your 10s, the number on the right side are your 1s. And then it's a way to basically organize your information. Kind of like a dot plot. You see all of the data, but it's just represented in a slightly different way. You could do the same thing for decimals. You could take 2.1, for example, and on your stem and leaf plot, you could have 2.1, and the key here is that 2.1 is 2.1. So the numbers on the left are the ones, the number on the right are tenths. Okay. All right, time series, I'm going to skip that also. Really, the big ones here, the dot plot, the histogram, stem and leaf, those are probably the three big ones. You'll see frequency polygons from time to time, but really dot plot, histogram, and stem and leaf, those are the three that we're going to see most often, especially as we work through these lessons. So, all right, so that is it for chapters 1 and 2. Again, as we kind of wrap up this first lesson, just thinking about, the type of data we collect, thinking about how you collect that data is important. Make sure that it's random, make sure you're getting a cross-section of the population through your sample. If you want to show causation, setting up that experiment and using that experiment in a way that, again, mitigates those confounding factors. And then as you synthesize all of that information, that data that you've collected, those results that you've collected, how are you presenting that then to your audience? What types of graphs, tables, visualizations are you going to use to make it clear and easy to digest for that audience? All right, that is it for that lesson. I look forward to seeing you in the next. Take care.